Okay, I'm talking about 2. Just go to 2. Two is more important. Yeah. So see, of all the children in the school, how many were examined? There is a question. Now, we will find that the first year, the examination coverage was better. Does anybody have the answer for that? See, and the second year? Right, slightly lower. Now, what is the percentage we are talking about? When I went to the school, did I see all the children? No. What percentage did I see? But why the hell am I asking that question? What is the importance of the question? Give an answer. You give an answer. Why should we ask the question of all the children in the school, how many were actually examined? We are discussing exercise number 2.
These could be the only children who are available. There could be people who are on.
Correct. But why is somebody asking that question? How many did you examine? Correct. I'm looking for some sort of a problem of leprosy in a community. I went there and examined only 20% of the children. Is that good? No. Only 40% of the children. Is it good? Then tell me, what would be a good percentage? Ideally 100. We can never get 100. So what we do is we hope we are as close to the 100 as possible. The worry is this. I want to start thinking this way. Were the children who were missed during the survey different from the ones you have seen during the survey with respect to leprosy? This is always your worry. If they are different with respect to leprosy, then you are getting a different estimate. And this is always the problem with looking for prevalence data. How close to the truth are you? And that question bothers you. Now, let me tell you something else that happened. We also wanted to get rid of rheumatic fever. Have you heard of rheumatic fever? Rheumatic fever is a condition which starts with joint pain, but also affects your heart, and your valve gets damaged. Now, it's an ugly disease because children who are running around, playing, suddenly start developing breathlessness, and they can't run. And most of us, as physicians, hate the disease. But luckily, we know why rheumatic heart disease comes on. Why is that? Streptococcal sore throat. Simple enough. And streptococcus is very sensitive to penicillin. And there's one particular type of penicillin, we call it long-acting penicillin. One shot you give it, and it will take care of the infection for 21 days or 28 days. Except that your gait changes after that, You have a limp for a few days. So we went to the schools and decided to protect our children from this ugly disease called streptococcal disease. So when we went to the school, each school had a particular day to go. We'll call out. Anybody with sore throat? First time they said, yeah. Show the throat. And we looked for signs of infection, and we found infection, they got a shot. Children quickly learned. Next time we went, anybody got sore throat? Said, open your mouth. And we found we gave a shot again. Children learned even better. Next time they knew, if it is so Tuesday, And if you have a sore throat, don't go to school. Now we are wondering whether something like that happened here. Not in leprosy. Childhood leprosy is a harmless thing. It comes as a patch. In fact, we encourage boys to take off the shirt, examine each other. And the ones who have a shirt, the others will bring him there. Sir, I got a patch. And this fellow looks very, so, he's not embarrassed. He's got a patch, he's special. We immediately take down his note detail and give them some tablets. And he's special, so he doesn't feel stigmatized. So I don't think they were running away from because we were coming to survey them. I don't think. But we will consider that as a possibility throughout our exercise. The second question was, what was the prevalence of leprosy in the 2 years? We're talking about 85 and 86? Huh? 85, we examined some people, and there are some cases of leprosy. Do you know what the prevalence was? Did anybody calculate? Let's talk in thousands, per thousand. So we have numbers like this. 48,000 were examined in 288 cases. 288 divided by 40,000. So whatever that is your prevalence of leprosy. That is simple. But in 86, a little more calculation you have to do. How many were examined? 46,000 were examined. And how many cases were there? 46 plus 40 plus 80. The 200 are inactive, that means they are cured. I told you, many people with leprosy get cured on their own. So there are no more leprosy. So you get the prevalence for 85, prevalence for 86. Now there's a question on what are the incidents of disease during the 1 year of study. For that, we need a numerator and a denominator. Now we are looking at incidents. That means new case emerging. New case emerging. How many new cases emerged in a previously disease-free population? That is the question. So you have to have a numerator, new cases, and your denominator is previously disease-free. With 1 year follow-up. Remember, unless there is a period of follow-up, you can't calculate incidence. All right? So you have to first carve out from the data a population you know are disease-free and has been seen both last time and this time. So write down the equation in this fashion and tell me what is the numerator, what is the denominator. So tell me what is the group we saw both in 85 and 86. Some children were seen both in 85 and 86. They are called the re-examined children. That is correct. That is 40,000. But we know also something else about the 40,000. Some of them were previously having leprosy. Foul, you can't count all the 40,000. Are you with me? Because you can't. So you minus from that, how much? 200 and
288. So 40,
200 minus 40. Not 288. Some of the numbers came back in the 288, but the 240 came back. So that is your denominator. And what would be your numerator be? 80. That is your incidence of leprosy. There are some chaps who joined the school later, or some who didn't come last year in the class, but this time they have come. How many of them were that?
6,000.
6,000 of those. Did some of them have leprosy? How many of them? 46 had leprosy. When did they get the leprosy? We don't know. But we know when these fellows got the leprosy. These 80, we know exactly when they got the leprosy. So we have a clean numerator, a clean denominator, and the best estimate of incidence for the duration. Are you with me? Please don't take something for granted.
We can do it other way also. No, for 40,000 we already know the prevalence. So it comes the same way.
How did it be?
We had the prevalence of the previous year. In this 40,000 we know the prevalence. We can just subtract that.
Incidence.
No, out of those 40,000 whoever had, we had calculated in the first part. So
But that is the 288. But here we are actually following up individual children. So I know the information who was seen last time, who was seen this time. Some of them didn't come back second year.
The prevalence will be still per 1,000 same.
Yeah, but the numerical value of prevalence changes each year.
Each year it changes, but
Yeah.
out of them, the total who had will be the same.
What will it be? Tell me the number.
The same actually.
I mean, you got the same answer different way. Okay. Now, there are some tricky questions on this, underneath that. Can you read out the question?
And the estimated prevalence and incidence rate is said to be applicable to A, the entire group of school children, B, all the children in the area belonging to 5 to 4 million.
When you do survey and come out with the results, in a cross-sectional study, the most important thing happens to be to what extent I can trust the result. So the fact is, I want to know prevalence and incidence of leprosy in the school children. But what is the method I used? I didn't go to every child in the community. I went to children to school. Shortcut. I can finish it in short time. But is it applicable? That's the question I started with. How different is the prevalence or incidence in the community as compared to school? So, to sort it out, I'm going to make a statement. Listen to this carefully. Children in the poor families tend to be more often absentees in school. You agree with that? Children of leprosy patients belong to poor families because the parents have leprosy, and children of leprosy patients also have a higher risk of leprosy. Now, if you put all this argument together, suddenly you get the feeling the ones who didn't come regularly to school or drop out are more likely to have leprosy than the children in the school. So very often, you don't have the actual figure. You figure it out kind of logically and then say, oh my God, this may be far from the truth. I may be having a highly selected population. I have a small area in Vellore where I used to work regularly. This area was notorious. All the people had a criminal record. They are pickpockets, stabbing, murdering, all things. That also happened to be the center of all commercial sex workers. Okay? And I worked with these girls who are about, altogether, I think we had about 180. Vellore is a small town. And that area had about 180 commercial sex workers. And so I was interested in asking the question, all right, they have HIV rate very high, but what about others? The commercial sex workers come to me, so I know their rate. What about the people? Supposing I go and say, come one, come all, we have got a free HIV kit. We will test for HIV. Come. And about 70% come and say, sure, test. And the 30% say, all right, not all right. 90% come and say, check me. And 10% say, what? What test? AIDS. Oh, no. Is my 90% any good? No. So don't go by percentages. Percentages are useless. If it's a good coverage, it should stand to reason this must be a good coverage. There's a disease called glaucoma. Have you all heard of it, glaucoma? Anybody who hasn't heard? You all heard of it. You slowly, quietly, without any problem, slip into blindness. By and large, 99.9% of glaucoma have no symptoms until it is very advanced. I wanted to pick them up early. I invited them to our high hospital for a checkup. There are types called angle closure glaucoma, open angle glaucoma. Call them. You know how many came? 50%. Other 50% said, you think I have no other work? But will I trust that 50% results? Absolutely. Because there's no way glaucoma itself could have made a difference whether a person came or not. You understand? There's no way that would have affected the attendance at the clinic. So I was safe in assuming whatever I found is easily generalizable. And there's a last convoluted question. You want to read that? Yeah.
At the second survey we conducted in 1987 to 1986, and X number of new cases being rejected from N number of re-examined children, what would be the formula for annual incidence?
Numerator we know, X. What should be the denominator? Simple. We want annual incidence. So what would be the denominator? If I put N, yesterday we discussed, it will be 2-year incidence. If you want annual incidence, you should put a 2 in the denominator. Hello? You lost? I know that question is kind of convoluted. There are X number of cases occurred in how many years? 2 years. How many people have followed up? N number. In the N number, 2-year incidence was X. So, if you want annual incidence, you want to annualize the incidence rate. You annualize your interest rate in the bank. So that is the equation. That can't be too tough. But the second question is tougher. Will it be same as the one we calculated now? Or will it be higher? Or will it be lower numerically? That's a little more tricky. It'll be lower, you say. Why?
Because we are dividing the number of cases by twice the number of the followers.
Yeah, but they had the twice the number of time. Right? So if the rate is constant, why shouldn't that give you the same result? Except one problem. Is there self-healing in leprosy? Yes. So some people develop leprosy and heal within 2 years, and we never see them. So this number has to be lower than that number. These are all practical problems in measuring incidence of disease. Whether it is cancer, whether it is heart disease, same problems recur. I'm using leprosy because I'm comfortable. Okay, maybe you are not so comfortable with leprosy, but there is quite a lot. I used to get this beautiful case of leprosy. The doctors have a way of saying this. Beautiful case of leprosy. Who will describe leprosy as a beautiful case? Only medical people. We were having a discussion in a hotel. This is after a meeting on diarrheal disease, rotavirus. After that, the manager came in. Could you talk a little softly? We were talking about diarrhea, and all of them are trying to have the lunch. So really, medical people are quite antisocial in that way. But they have this beautiful case and say, next month I have a case of a class for a medical student. Get this case from me. Come there, clean, gone, absolutely healed. So, that is the problem here. All right. Now, I'm going to do a test, okay? You have to listen to this very carefully. There are 5 questions, and all you have to write is 1, true or false, 2, true or false, 3, true or false. Okay? So finally, I'll ask you how many true you got, or whatever it is. So you just answer it. Okay? Is it clear? I don't want to know what your answers are. I just want to know group average. But you have to listen to this very carefully. Question number 1. A survey for malnutrition was carried out. Childhood malnutrition. The report says 3rd degree malnutrition is 10% prevalence, and 95% confidence interval is 8 to 12%. Have you heard that? The report says. This means that if the survey was repeated 100 times, the results will fall within 8 and 12%. True or false? So first question, you write in a corner somewhere, confidential information, not to be shared with your neighbor, true or false. Got it? The second question has got a A and a B. Okay? So 2A, 2B. A diagnostic test has a sensitivity of 90% and a specificity of 90%. Have we got that? Now, A. This means that the overall accuracy of the test is 90%. Say true or false. B. This also means that if the test is positive, one can safely say that the person has a 90% chance of having the disease. True or false? Question number 4, because 3.2 has got 2 parts. A new vaccine for typhoid has been reported to have a protective effect of 90%. This means that the recipient of the vaccine will still have 10% chance of getting the disease. In a clinical trial, randomization helps in increasing the generalizability of the results. True or false? So you should say how many true. Okay. How do I count that? Okay. How many truths? Okay. 0 truths. Anybody? 1 0 true. 0 is 1. 1 true. 2 truths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3. How many truths? 1, 2, 3, 4, 5. 5, right? We're going to add up and see how many mysterious people are there who has no truth. 4 truths. 1, 2, 3.
That's going slowly.
Some half truths are there. And all 5 true. All right. Fair enough. So the somewhere in the center is this 12. 12 people thought, okay. Now the answers. The first question was about the 95% confidence interval. That was false. Okay? The second one was about the diagnostic test. Accuracy 90%, that is true. And then the second part is false. That is, you are 90% sure that it is. Then the third one was 95 protective effect. That is false. Okay? That is terrible sounding, right? Well, most people have voted for true, that's false. And finally, I know. What is the other question? Randomization. No, it doesn't help in improving generalizability. So it's false. So actually there is 1 true and 4 false. Okay? Okay. I feel comfortable because I need to be there. I need to take the class. You understand? Suppose you all had answered correctly. How does it work to teach them, right? So thank you. Now, yesterday I taught you what is called as the risk of disease, cumulative risk of disease. And we did a survival analysis and calculated. I hope it has sunk in your mind and you know something about it. Because it caused a lot of problems. Whenever we go for meetings and see, everywhere we go, we are called experts, okay? We call each other experts. And that causes the biggest problem, okay? So last time we got into a big fight about how these things are done. And the problem is, when somebody say, people who have been treated for breast cancer, and then you look at the lifetime risk of dying of breast cancer. Treated with breast cancer and lifetime risk of, it's fairly large number. And what do you mean? Dying of breast cancer is so high. The lifetime risk of dying of breast cancer can't be high. You die of other things. You die of heart disease. You die of railway accident, whatever. No. The problem, the way you calculate is, you remember yesterday, all other deaths are excluded. They are all shown as withdrawn. So the cumulative incidence of the disease that we calculated is conditional on that you don't die of any other disease. So that causes a problem for people to understand. That value is difficult to comprehend the moment you expand it to lifetime experience. On the other hand, 5 years, 10 years is more comprehensible. Why? Because we have an inner feeling as to what is the risk of death. But the moment you convert into lifetime, it looks horrible, especially in the equation that we use. So you should be very often. Yesterday I talked to you about incidence rate and the problems related to the whole lot of things. Today I want to warn you about this because I forgot to tell you yesterday. That's it. Now today I'm going to shift from the disease frequency into something else. And that is to do when you measure things, incidence, prevalence, blood pressure, whatever you measure, how do you know you're measuring it accurately? You're measuring it well. You can be trusted. And then the classical teaching is every measurement should have 2 qualities. They are validity and reliability. And that question, it keeps coming back. And very easy to ask the question. Not very easy to, establish these things. And you need to be quite ingenious as to how you do it in different situations. Let me give an example. A new glucometer came around. This measures blood sugar very easily. You don't have to go to the lab, sit at home and measure it. But is it a good instrument? Is it as good as a lab? So what one of the students they did was, took 100 people, measured it on a standard method in a lab and on a glucometer. Got all these values. Wow, 100 here, 100 here. And did the Pearson's correlation coefficient. And you know what she got? Plus 0.99. Plus 0.99. Have you heard of Pearson's correlation coefficient? It is the range +1 to -1. +1 means absolute positive correlation. -1 means absolute negative correlation. She got +0.99. She was quite thrilled. This means that glucometer can actually be used instead of the lab. Right? Wrong. That is not a measurement at all. Pearson's correlation coefficient does not measure agreement. I said this because there are a lot of traps in understanding the reliability of and validity. So let us go through briefly that. One way I remember, my wife bought me a pair of pants. It was ghastly looking. But did I tell her that? No. What she said? You like those pants? Sure, I do. 2 days later, she said, you all like my pants? Yeah, very good. After 1 week, she said, you know the pants I bought you the other day, you like them? I like them. You know, I was being consistent. There's one quality in a husband you require, be consistent, okay? And that's all the reliability about. If you get the same result from a machine repeatedly, you are reliable, you are consistent. But then she did something nasty. She said, if you like them so much, how come I never see you wear them? Now that is a mean cut, okay? She brought another standard to check my validity. How close to the truth are you? That is the question, validity. So reliability and validity are different kind of thing. One measures just consistency, repeatability. Other one talks about how close to the truth are we. Now, as you can imagine, the reliability check is generally okay. I gave you a bad example of Pearson's correlation coefficient. But there are easy methods of doing it, and in the handout I've given you that. If I have time, I will also explain to you. But validity is much more difficult to comprehend, measure. But before we go into that whole exercise, we have to accept one thing. Normally, in life, there is a variability. If we all looked alike, talked alike, smiled alike, what a boring world it would be. Okay? But there is a variation. And unless you understand what is the normal variation, this whole concept of repeatability, reliability will go haywire, because you will say everything is different and I can't make out. So to bring an order into this consistency issue, you need to have in biology a notion of what is the fundamental biological variability. And that is important to understand. And so in general, when you look at any characteristic, you ask, anytime a data comes to you, you ask two questions. Hey, what is common about this set of data? And that's where you stand up with things like mean, median, mode, and things like that. And then you ask the second question, what is the variability? And these two things simultaneously have to go into your mind. The commonality and the variability. And then you get hold of the whole data set in your mind much more comfortably. And I want to look at the process with you, because this is actually the building block of any research methodology, and it has to be said now and not later. So I'm going to start with a data set of 5 birth weights, okay? And for make it simple, the first child's weight is 1 kg, 2 kg, 3 kg, 4 kg, 5 kg. That is the birth weights. Okay? So I'm going to call them xi. Why do I call them xi? Because everybody calls them xi. Okay? So I have no choice but to call them xi. And how many are there? 1, 2, 3, 4, 5. And the first I said is we find some sort of center. The central value, the median, is 3 kilograms. If you add up the whole thing and divide by 5, you get arithmetic mean. That would be, again, 3. So sigma xi by n is equal to 3. And that is called mean. X bar, again, is a standard notation. So once you get that, you say, this is somewhat. Now you should not be too, strict about always looking for center. We used to have a statistician. He did not know how to swim. So he approached a river and he realized he very wisely asked the fellow standing there, what is the average depth? It said 4.5 feet. He was 5.5 feet. He walked across. We never saw him again. But what should he have asked? Maximum depth. So don't get fixed on the center. Sometimes you are, okay. So we have now to start with this. And then we also know there's all variable, highly variable. How do you kind of crystallize this variability? And somebody said, very simple, take the biggest value minus the smallest value. What do you get? 4 kg. And 4 kg is your range. Terrific, range is that. Now I'm going to give you another set of values. Okay, watch this. This is 1, 3, 3, 3, 5. What does that mean? 3 kg. What is the range? But tell me, which is more variable, this or this? This is more variable. Somehow this range doesn't tell the whole truth, right? It's a very wishy-washy fellow. So we are kind of scientific people. We need better methods. So somebody thought for a long time, hey, let's do one thing. Let's ignore this fellow. Okay. Let's take the variability from the mean. Got it? Take everybody and say, how far are you from the mean? How far are you from the mean? And that's called the dispersion from the mean. And take the dispersion from the mean and average it. You get an average dispersion. Such a simple thing. I wish I had thought of it. So what do you get here? From the mean, xi minus x bar, minus 2, minus 1, 0, plus 1, plus 2. I found the dispersion from the mean. Now you add up. What do you get? Oh gosh, you get 0. That is the problem. Every time you take the dispersion from the mean, you get a 0. So our bright idea doesn't work. But I remember somebody suggested, why are you worried about the signs? Plus, minus, don't need. You ignore that and add up. In fact, old version of Park and Park used to have that calculation. It means that doesn't matter whether I owe you money or you owe me money, right? Wrong. That matters, right? Okay. So this is not allowed. Park and Park should not have put this stuff on the textbook. You had a name for it also, and I won't tell you what the name is. Somebody else came along and said, hey guys, just square it. What is the advantage of squaring? The signs disappear. Mathematically, you are perfectly all right. Now you can add them up. If you add them up, what you get? 10. So I get something called, so sigma xi minus x bar squared divided by n will give you 10 by 5 is equal to 2. That is called the variance. A very central person in whole statistical analysis. The whole family of analysis of variance all comes with this little zero. Okay? So you should know it, because without that there is no statistical analysis. Now, one problem here. We know what our mean is. What is it? 3 kg. What is the variance? 2 what?
kg squared.
2 kg squared. What an ugly figure. I don't like to be described in kilograms squared. Would you? No. You can't even conceptualize it. It's sort of some kind of a terrible. If my height is given in squared height, will you recognize me if you see me? No. So that is the problem with variance. Otherwise, it's all right. Mathematically, no problem. But socially, in communication, it's ugly. So somebody said, listen, don't walk around these squared fellows. Just find a square root. Ha! You find a square root for this, that becomes square. And that is called standard deviation. And do you know why they call it standard deviation? No, I also don't know. But somebody called it. Okay? And because they called it, we call it standard deviation. And people are wondering why the square root and all. But suddenly it emerged, the standard deviation is a brilliant statistic. It can do really magic. And I'll introduce you some little things what the standard deviation can do, and that is phenomenal, and it changed the way we look at data. I know none of you look at the standard deviation, right? But it is in the article when you read, you look at the mean. Poor standard deviation, everybody ignores. But that fellow is important. I'll tell you why. When I go to Bangladesh, I feel I'm a very tall chap. Because Bangladeshis in general are short. So I look very tall. Then I go to Netherlands. I look very short. There are even women taller than me. And I'm not used to talking to women like this, And if you get in the lift and stand next to them, it's very uncomfortable. Now the point is that when the mean for Bangladesh is somewhere here, okay, with a variability. And Netherlands is somewhere there. Mean shifts. What about standard deviation? Same. Looks like there are two phenomena which affect your characteristics: nature and nurture. Nature means what you are genetically programmed with. And that is reflected in your variance and standard deviation. But amount of milk you drink or amount of food you eat may vary. And that will affect your mean. Means change. And standard deviation remains constant. This constancy of variance is a fundamental principle of all statistical analysis. Okay? People come to me for calculation of standard sample size. And we need standard deviation. Where do I get a standard deviation from? If you find one standard deviation is equal to all of the standard deviation. The variation in standard deviation is usually a function of error in measurement. If something is accurately measured, you will get nice rounded standard deviation which is small. The moment you become lackadaisical and you are become error, then your standard deviation go wide. So when people judge your article, They don't look at your mean, but they look at your standard deviation. And then you realize they can figure out how meticulous you are in your measurement. You understand? That's why it is important. Most of our characteristics, when you look at height, weight, cholesterol, you name it, practically, you look at human population and the distribution is something like this, called a normal distribution. Again, don't ask me why it's called normal. Somebody called it normal, we call it normal. But the basic argument is simple. Values tend to crowd around mean in a given population. They tend to crowd around mean. And then some give extreme values this way, some give extreme values that way. It's so smooth. It's a function of, I told you, the gene mainly. And that is a reflection of our biological variability. When you have highly inbred mice and all things, these biological variability comes down. They become very narrow. But luckily in human population, we still have some variability left. Thank God for it. That variability is important. Okay? The other day, somebody came from Finland. Do you know where Finland is? You're thinking about it? No. It's very close to the North Pole, okay? Hardly anybody. So this guy is coming to India first time. He saw me in my hospital in Vellore. I work in a community health hospital. He came, looked at me and shook his hand and introduced himself. And I said, I'm so-and-so from Finland. I said, hi, I'm JP from Vellore. Then he went through this door, came out to the other door, and he saw me. He grabbed my hand and shook hands again. I'm so-and-so. In the next half an hour he was there, he introduced himself to me about 5 times. What is happening? To him, all Indians looked alike. Okay? And he was not taking any chances. He pumped everybody's hand. Okay? Now, I could appreciate it because I was once in Vietnam. And in Vietnamese, all looked alike. And I went to this place and the lady was helpful. She gave me all the dongs, they call the money, and showed me where to stay and everything. I came down the stairs and went out, and she was standing there and I said, hi. That one gave me a tough look. It's a different one, but they all looked alike. So the problem is this biological variability is sometimes not easy to comprehend. For example, to us all crows look alike. But the crows know which is a Jack crow, which is a Jane crow. They know among themselves. So don't get fooled by this notion. The way you measure, way you quantify may be different. But this normality of everything from your height, weight to any parameter is their underlying whole thing. But if it is normally distributed, which most biological characteristics are, then the standard deviation comes into play brilliantly. It becomes a tool to measure and predict things, because one standard deviation on either side of the mean will have 34 and 34, 8% of the subject within that. Okay? So if you take a sample of population and you measure a mean and a standard deviation, we are now predicting about the whole population. 2 standard deviation include 68% of the population. And about 2 standard deviation either side, 95%. True statisticians don't like it. They have to be more accurate, but I say 2, it's actually 1.96. Oh, forget it, okay? Doesn't matter. But this will tell you, now I'm going to give you this part, and the danger of listening to me is suddenly your brain become numb and you don't think. So I want you to think, all right? I'm going to give you a mean birth weight and standard deviation. And I'm going to ask you some questions. Let me see whether you can answer. Mean birth weight, 2.8 kilograms. Standard deviation, 300 grams. All right? Assume normal distribution. Assume birth weights are normally distributed. So I got 3 questions. Will you take it down? What proportion of the babies are more than 2.8 kg? What proportion of babies are less than 2.5 kg? What proportion of babies are more than 3.4 kg? 3 questions. Can you answer it? All you need is this diagram and this information. Can you answer now? What proportion are above 2.8 kilogram?
47.
How did you get that?
50%.
If it is normal distribution, mean will be equal to median. Where did you get that number from? No, this one. I'm talking about 2.8 kilogram is the mean. If a normal distribution, mean and median are same. So above 50%. What percentage are below 2.5?
16%.
So now we have to calculate. 2.5 is 300 grams below 2.8. So that means 1 standard deviation. Now this part is 50%, this is 34, so this must be, the remaining must be 16%. That's correct. What about 3.4 and above? Okay, this much is 2 standard deviation is 95%. This plus this 5%. So this must be 2.5%. This is 2.5%. Only thing is my diagram is not proportional. Anybody who objects to what I am saying? No. So, what we have learned is that the standard deviation is constant. Number two, not always, but biological situation. And if something is not normally distributed, then what happens? Then SD doesn't predict this way. It's a problem. SD will try to do its best. But, for example, let's say you've got a distribution like this. If you put two standard deviation, you'll get something like that. With this person's whole thing being 5% here. And this will go into some sort of a unknown territory where you can't measure. Okay? So that is uncomfortable. But this is where you have to ask. Many of our serological titles, everything, are distributed that way. So are you saying, then don't use standard deviation there? No, you can use it. The thing is, you are measuring it with a scale. That scale is your creation. Remember, we discussed mathematics is a human invention. Who asked you to count 1, 2, 3, 4? Why don't you call 10, 100, 1,000, 10,000? That's another scale of measurement. You got log natural scale of measurement. Now the moment you convert into that, this thing disappears. It becomes a normal distribution. Bingo! That's why we still pay our statistician salary, They'll do all this transformation and do it for us. So, but that is, we don't have to worry about. The basic principle is, there is a biological variability, and the way to measure is using a standard deviation. And that gives you ability to predict. And the constancy of standard deviation encourages us to know that the underlying factor is purely biological. So whenever you see standard deviation going all over the place, I'll give you two examples. I was looking at the blood sugar values from Vellore area. I looked at the 20-year-olds and mean blood sugar and standard deviation. It was nicely distributed. Standard deviation is normal, everything. As I started going up the age, the standard deviation became fatter and fatter and fatter. Why is that? Because with old age walked in a new disease called diabetes. The population was no more a single population. It's a mixture of two populations, diabetics and non-diabetic. And the first thing you notice is standard deviation become fat. It's a dimorphic distribution. So SD gives you a diagnostic clue about all these patterns if you only pay attention. But our problem is we never look at SD, we ignore it. Okay? Now, I'm going to give you a last question before I change the subject. Figure out in your mind. I have measured some children and I have given you the weight, mean, and SD. Weight, the mean was 20 kg and SD was 2 kg. Height was 100 centimeters, the same children, and 100 centimeters, and SD was 5 centimeters. Now, question to you is, these two biological parameters, which do you think is more variable, height or weight? Height is more variable, weight is more variable. Shall we vote on it? Height is more?
Height is more. Yeah.
So, how many think height is more variable? How many think weight is more variable? Weight is more variable. He is saying weight is more variable. But how do you do this? You see, I walked you into a trap. I asked you to compare oranges and apples. One is in kilogram, other one is centimeter. And you ask this question, which is more variable? When you fall into a trap like that, you should know how to extricate yourself. Ignore them thing. You should find out something else. And you answered this, and I agree with you. But why did you say it is 2 kg?
The difference, the height is mandated or dictated by the genetics, while weight is dictated by the nutrition.
He brought in extra information from the side. All right. Any other reason why somebody said, yeah?
The proportions are much different as compared to the fraction. The fraction is much lower as compared to the the fraction is much higher.
Clever. That is clever. She wanted to avoid the kilogram centimeter story. So she asked the question, what percentage does this become? 2 by 20. Sorry. It become 10%. This one is 5%. Standard deviation as a percentage of mean, it's called coefficient of variation. And this shows this is more variable than there. A very useful thing to remember. I taught you this because when you see the coefficient of variation, you also know whether something is normally distributed or not. If a coefficient of variation is usually for most biological things less than 25%. The moment it hits 50 plus, then you know it is not normally distributed. Can you remember that? Statisticians have designed a whole lot of tests to see if it's normally distributed or not. But you guys won't do it. What will you do? You look at the coefficient of variation. If it's less than 25%, say, yeah, I think it is normally distributed, very confidently. If it's more than 50%, I'm sure this is not normally distributed. Suppose in between that, look the other way, don't answer the question. Okay? That's a difficult area. Call for the help. So that is the matter. So I want you to take into this exercise called exercise 9. It's very simple. It has got 2 pages. So start doing both. Guys finished? We are stepping into this whole concept of validity, and the easiest format we teach is in the form of a diagnostic tool. Truth. Truth is what we are after. So the classic example, when you go to a court of law, they ask you to, they make you swear. Not at the judge, to swear saying that I will the truth, all the truth, and nothing but the truth. Why all this extra line? I'll tell the truth. Isn't that good enough? All the truth and nothing but the truth. It's obvious. When you tell all the truth and make a few stories extra, nobody will know which is the truth, which is not the truth. So you have to have these two compartments, all the truth and nothing but the truth. All the truth is what we call in epidemiology sensitivity of a test. And nothing but the truth, we call it specificity. So if you look at your exercise, we already told you the truth. When you learn something, you can't have everything unknown. So here I've told you 900 of them have disease, 900 don't have the disease. So truth is known. Now we want to see how the test is performing given that we know the truth. We expect all the 100 to be test positive, but that didn't happen. Okay? So this 90 became positive and they actually had the disease. So they are called the true positives. And what about these? They are falsely negative. They are negative, but they are falsely negative. So sensitivity is actually the probability of tests being positive among diseased people. The 100 diseased people, 90 were positive, so we call it sensitivity of 90%. In the case of people without disease, we don't want any of them to be positive. Nothing but the truth. So we want all these fellows to be here. These 810 are negative, and they are truly negative. They are called true negative. But unfortunately, these 90 fellows went the wrong way. They decided they will be test positive. They are called the false positive. So, the question in specificity is, of all the people without disease, how many were truly test negative? So the equation has to be read not as letters, which means something. Probability of tests being negative given there is no disease. Okay? And ideally, this should be 100%, this should be 100% here, and then you have a perfect test. Step 2, when I sit in the clinic, I don't know what the sensitivity and specificity. What I hear patients coming to me with saying, "Doc, test is positive, test is negative." Now I have to interpret the results. I have to say, oh, you have the disease, you don't have the disease. Let's take somebody comes to me with the test positive. In this case, I'll say, what? What should I say? Given that I know the table, what is the probability the person has the disease? Anybody who comes with a positive result, what is the probability he has the disease? 50%, just like our weather forecast. It may or may not rain. So you tell him, smile and say, you may or may not have the disease. He'll be very happy. So that is called the predictive value of a positive test. And in this case, as a clinician, I would say, that's pretty poor. Predictive value of a positive test is pretty poor. What's the point in saying, that fellow already knew he may or may not have the disease. And after the test you say you may or may not have the disease. Waste. But here, if the test is negative, things are brighter. 820 people were test negative, and most of them were actually disease free. And that we call it the predictive value of a negative test. We say 810 divided by 820 is the negative predictive value. So that is how this is set up. Sensitivity, specificity, positive predictive value, negative predictive value. You all know this, and you did the last sum also. We said, we take you to another hospital where people are different. There 500 have the disease and 500 have no disease. When the test is done, what will happen to this 500? The same percentage will be positive. How much? 90%. There will be 450. This is 50. What about here? 450 will be, because this is the same test, same disease. So you'll get the same 90% sensitivity and 90% specificity. Now let us see how many test positives are there. 500. Here 500. And what is the positive predictive value? 90%. Now you are a smarter doctor. When the guy comes with a test positive, you have the disease, boss. You better have treatment. How unfair. One hospital you behave one way, another hospital you behave another way. What made the difference? Prevalence. What is the meaning of prevalence? How will the doctor know the prevalence? I'm sitting in a clinic. Do I know prevalence of all diseases? In fact, no doctor knows it. You ask them any question, they don't know. Now, how the hell do they manage? So I'm going to reword this prevalent. This prevalent, actually in a clinical setup, is what you call probability of disease even before the test is done, is the gut feeling of the doctor. Okay, pre-test probability. Pre-test probability of the disease is what the prevalence you are talking about. And clever physicians always make use of pre-test probability to judge the test result. Without that, you can't make out anything. So you should know, is it likely to be a case? How likely is it? So, in this equation of 500, what all went in? There are true positives and false positives. True positive is a function of sensitivity. False positive is a function of specificity. Okay? But the main actor is your pre-test probability. The gut feeling that the doctor has, the person has the disease. Here, the pre-test probability was 10%. Even before the test is done, there's only a 10% chance the person has a disease. Here, it's 50%. I know it is a little difficult to comprehend this pre-test probability and things like that. What we want to know is the positive predictive value or the post-test probability. After test, what is the probability the person has a disease? I remember one day I was sitting in an OPD, and in Vellore, in my hospital, we have a kind of table where one end a senior sits, the other end a junior sits. So I can keep an eye on him and he can keep an eye on me. Perfectly safe. So, so here comes a girl. She was 23 years old, married for 6 months, and she is missing her periods for the past 3 months. Does anybody have a problem making a diagnosis? No. It's very obvious. But still, I looked at her seriously, held a pulse. You know, in Hindi movie, they always hold the pulse. And then I took a slip of paper and then wrote there, pregnancy test, and gave it to her. She went to the lab. A little later, she came back. She had seen the result written positive in green letters. She was an educated girl. She knew what's happening. She was all excitement. Her hand was trembling as she handed over the paper to me. So I read it seriously. I said, "Congratulations, you're pregnant." And she grabbed my hand, thanked me so profusely. It looked as though I was responsible for the whole situation. And she had tears coming down her ear. And the intern sitting next to me was moved. But I had to go away, and another lady came. She had a different story. Her story was, she is 48 years old. She had tubectomy 25 years ago. Now she is missing her periods by 3 months. My intern knew what to do. He took a slip and wrote, pregnancy test, and gave it. Believe me, as luck would have it, it came as positive. So he told her, "Congratulations, you're pregnant." She almost bit his head off, okay? And she couldn't understand what he had done wrong. He has done wrong in measuring the pretest probability. In my case, the pretest probability way up there. Even if the test had been negative, I would have said, "You're pregnant." Okay? Remember, I felt a pulse already. Okay? Now, this is an extra bit. So actually, we as physicians work on the pretest probability before we do the test. A person comes with fever. I don't grab him and do a Vidal test for typhoid. No. I ask him question. What do you do? I'm a cleaner in a lorry. I travel all over the place. How long is the fever? Nature of fever. And I examine. I feel a small, soft spleen. Look at the tongue. I say, there's a pretty good chance of it being a 50-50 chance of it being a typhoid. I do a Vidal. It's positive. Now I am sure it is Vidal. So the whole game plan, when you look at this, the truth is a function not only of the test, it is also a function of the pretest probability. And that is where the difficulty starts in establishing how the validity of this test, because it's not always in your hand. And when you come back from coffee, we'll discuss how do you manipulate this nebulous thing called sensitivity, specificity, and post-test probability. One has test 1 has a sensitivity of 99% and a specificity of 90%. Test 2 has a sensitivity of 90% and specificity of 99%. What should I do? Which should I select? I can't do both. Test 1 or test 2? Test 1 or test? Breast cancer. Test 1 or test 2?
That will depend on whether it's a screening test or confirmatory.
Screening. Screening test. That is, I am going to go to the community and screen for everything.
Sensitivity.
I can't hear. Say it with confidence. Whether test 1 or test 2. 2. Some 1, 2. You have this problem. The difficulty is that how do you make this decision? Is there a scientific approach to it? And so what happens first is that I've taken a difficult problem. Do you know what is the frequency of breast cancer is in our community? It's about 1 per 1,000 per year. So it's not a common disease. So it's rare. So what happens is, we already found the pre-test probability is low. So the post-test probability become low. So so basically what happens is, a large number of test positives will be falsely positive. Okay? Whatever you do. But in this case, you can easily say, if this approach, it will be a very large number of false positives. In this approach, the false positives will be less, but it will still be large. If you calculate it in 1 per 1,000. I presented this to say these decisions are very complex. Okay. Now remember, here there is an extra price to pay. When you say you are a suspect breast cancer, that affects the quality of life of the human being tremendously. And in fact, some people never ever recover from it. They become neurotic for life. So that's why you should actually enter into this whole thing very gingerly. So I want to take the first statement. In a rare disease, screening is basically a very dangerous proposition. Okay? People for political reasons start screening for cervical cancer. And in our country like ours, it's not easy. I've gone through this whole process. I'm telling you, it is quite upsetting to people. You destroy the quality of life. I told you I used to do this leprosy survey regularly, and some cardiologist came and told me, hey, JP, anyway you're going examining all these children, why don't you also auscultate? If there are murmurs, send them to us, we'll do echocardiogram and then find out if there is any problem. Like an idiot, I said, sure, why not? Put a steth on. Lesson number 1 I learned is, if you examine 200 children with a stethoscope in a day, you develop acute otitis externa, okay? You have severe pain. That is number 1. Number 2, I gathered all these children and told the parent, don't worry, we'll do it free echocardiogram. Who wants free echocardiogram? Anyway, they liked me, they came with me. But the children changed. Children used to play football, hockey and all, they stopped playing. Parents started treating them differently. Heart case. I could never rub off the label. Okay, so now a cardiologist come and say, I want to get lost. You go yourself and do. Don't call me into this play. Problem is, this is not easy because the follow-up is difficult. And what happened was, practically every murmur I heard was a functional murmur. Okay. If one life I had saved into the whole process or found out early could prevent Eisenmenger complex or something like, I would have been happy. Nothing. So I hated it. So I'm telling you, I'm biased in the whole thing. But so I took. Now listen to this carefully. I've given you the problem. The final truth, the positive predictive value or negative predictive, is a function of the prevalence. That puts us in an embarrassing situation, number 1. In a hospital, things are a little difficult. You can figure out what the chance of disease, you're okay. Screening, you're in trouble, number 1. Number 2, if you get large number of false positives, that's a headache for you in most situations, especially cancers. And this happened with HIV testing. Early tests produce a large number of false positives. and we mismanaged it, and we always keep quiet about it. We don't tell the story, how many suicides we created and things like that. This all happened. But now I'm going to ask you one question. When anybody asks a question of screening, you ask the question back, what are you trying to do? Are you trying to rule in or rule out? Immediately the entire scene changes. What do I mean by rule in, rule out? The best example is HIV. There are two ways we do screening for HIV in Vellore. One is somebody comes and tells you a story about his escapades and his problem, and we do a screening. There, we are trying to rule in. Trying to rule in. What about in a blood bank? Blood bank, you actually don't care anything about the human being. He is trying to give you a blood. This blood, should it enter the blood bank or not is your question. You want to be absolutely certain every bottle you collect is perfectly safe. That is, you want to rule out. The whole attitude is different. And how does it impact our whole thinking? Now I'm going to make a statement. Listen to this carefully. A highly sensitive test, if it's negative, you can be certain you don't have the disease. I'll repeat it in numbers. A test with 100% sensitivity, if it is negative, then you know you don't have the disease. Okay? Statement number 2. If a highly specific test, if it's positive, then you have the disease. In other words, if a test is 100% specific and you are positive, then you had it. You have the disease. Do you understand these two? Think about it. 100% sensitivity, if it is negative, then you are in command. I don't have the disease. Similarly, if 100% specific test, it is positive, then you have it. And these two things, sensitivity and specificity, is a constant trade-off. You try to increase sensitivity, specificity drop. When you increase specificity, sensitivity drop. But if you are interested in ruling out, go for high sensitivity. If you are interested in ruling in, go for high specificity. All right? So now things are getting a little clearer. First of all, it has to be your intention to do this or that, and then choose the path. You can't hope to have everything in the world. Now, the question is, how do we do with the prevalence? We can't do anything. But can you manipulate your test system in such a way that you manipulate the overall sensitivity somehow? To study that, you have to do the next exercise, the one that comes after the one you just did. This is on diagnosis of tuberculosis. The one right after that, what is the number? What we are aiming to find is the sensitivity of test 1, step 1 and step 2, specificity, and sensitivity specificity of step 2. If you notice here, I got 900 disease free, 100 disease 1, of which 95 are picked up. So your sensitivity of the first stage is 95%. Or I'm going to write in this particular exercise everything in fractions. There is a purpose behind it. Can you understand that? I'm going to call it 0.95. That is a mathematician's way of doing it. They never put 95%, they say 0.95. Because manipulations are easier. What about specificity? What did you get?
0.88.
Point? After 8 what comes? 88, huh? That is the specificity of the test. Now we do something very sensible. We pick up people who seems to have cough for more than 2 weeks and then subject them to the next test. What is the test? Sputum AFP. So those who come here are all positive for the first test. And they take out the second stage screening. So screening is happening in stages. 1 followed by 2. And here, how many are positive? 84. And that means 11 are not positive. And here, the positivity is 104. And 85 and 105. So you got the sensitivity 2 of this test, sensitivity 2. Point 88 again, huh? Both 88, huh? You guys are sure, no? Not fooling me. No. Specificity?
0.99.
I need the decibels carefully. 0.9?
0.99.
9 or 98?
99.
So now we have finished it. We can calmly calculate the overall sensitivity. What do I mean by overall sensitivity? We started with 100 patients without tuberculosis, which information was secretly given to us. We wouldn't have known otherwise. And we landed up with finally diagnosing of the 100, 84 as tuberculosis. So the overall sensitivity is 84%. Do you all agree? Of all the TB we started, only 84 were finally labeled as TB. So the overall sensitivity, I'm going to call it sensitivity star, is equal to 0.84. Now I would like you to do one thing. Multiply 0.95 with 0.88. What answer do you get? 0.95 times 0.88. 186. Anyway, it should be exactly that. Our calculation shouldn't round off, but so basically what I'm trying to say is this overall sensitivity is equal to sensitivity 1 times sensitivity 2. We are doing a diagnostic test in a multi-stage screening. Here the screening is in series, one followed by other. And the rule is you are positive only if you are positive for both tests. That's a reading rule. You have to be positive for both to be positive. So we are going to ignore the stage first, those who are negative. No cough, no pulmonary TB. Right or wrong, don't argue, but that's the way we are doing it. But notice something. The first stage had a 95% sensitivity. Second stage is a 88%. Overall, it drops. Overall, it drops. Now, it doesn't matter which way it comes. S1 times S2 or S2 times S1, the overall sensitivity is always a product of individual sensitivity. It will be less than 1 and 2. So, those who think if you do the other way around, it will be better, no. Final answer is same. Because that we are kidding. Some will get caught here, some will get caught here. Overall, the product will be always same. Have you understood the importance of writing this equation? This equation says it doesn't matter which way you produce. Test 1 followed by test 2 or test 2 followed by test 1. As long as your reading rule is positive for both, then you are positive. What about overall specificity? Look at the two tables and tell me what is the overall specificity. Well, we started with 900 healthy individuals. Okay? We let 795 go home after the first round. At first step, we let them go. Second step, so altogether, we sent home 899 people out of 900. So overall specificity, SP star is equal to 899 divided by 900, which will be equal to 99.8. I want to sort of go above that.
998.
0.998. It's higher than individual specificities. So when you do this, the overall specificity goes up. Just make sure everybody follows what we're saying. Let's start with these 100 people. They all have disease, of which 95 were sputum positive. No doubt. The 900, some of them were sputum positive. How many? According to the story, 105. Okay? So the numbers are 95 and 105. And they are 200, they are taken for the second step. So where is the 114?
So actually then in second stage, all those who gave a positive history were subjected to a sputum examination. There were 85 tests positive, of which 84 were truly cases.
These are test positive column. 85 were test positive. Okay? Of which 84 were truly positive.
105 is 115.
That's how I made it.
115.
That's how I made it.
11 plus 104 of
Below 85.
That's how I made it.
Oh. I know it's a free country, you can do anything you want. All right. But what I want you to appreciate is this. When you do test in series, one after another, the sensitivity drops, but specificity goes up. Okay? Very high levels. For example, let's take there are two tests. Each one has a specificity of 90%. 90% specificity, 90% specificity. That's not great, but you do them in one after the other and put the rule, if both positive, then positive, the specificity will go up. How high will it go up? I'll show you with an equation. The specificity star is equal to 1 minus, take it down, 1 minus specificity 1 times 1 minus specificity 2. This is the equation. So you substitute 0.9 in these places. Do you know what overall specificity you get? Calculate. Can you see it? Do this first. 0.1 it will be here. 0.1 it will be here. 0.1 times 0.1 is 0.01. 1 minus 0.01 is 0.99. So your overall specificity will be 99%. Don't leave the room without understanding that concept. It's very important to know this is how its system works. We do it in HIV all the time this way. And please don't feel embarrassed if you don't understand. You know, it took me about a month and a half to understand that. And I'm asking you to understand it in 10 minutes. That's not fair, I know that. That is 99%. So you start with two tests. Each has a specificity of 90%. And overall specificity, when you test in series, is 99%. That is pretty neat. So imagine if you start with two tests, each one is 99% specific. Wow, the overall specificity will be astronomical. That's how we protect our blood bank. Okay? Not two tests, you can do three tests. You can be kind of obsessive about it, you know? Pretty neurotic. Now, I found a way to increase the specificity. Can I similarly find a way of increasing sensitivity? Sure. There is a method. Can you figure it out how it is? That's right. Change the reading rules. Test everybody for both tests simultaneously. And then you say, any positive, you're positive. So the guy with HIV will get caught either this or that. Difficult to escape. So sensitivity goes up. So for completion, I'll write the equation for parallel testing also. So write this down. Overall sensitivity in a test in series is S1 times S2. Overall specificity is 1 minus specificity 1 times 1 minus specificity 2. This is for testing in series. Now shall I change over to testing in parallel? The rule here is any positive, positive. Parallel testing. Overall sensitivity is equal to 1 minus S1 times 1 minus S2. Overall specificity is equal to SP1 times SP2. Luckily the equations look similar. You just have to know when to use which one, and there you are. So now comes the question. The way you use tests, it all depends on your ulterior motive. If you want to rule out, you need high sensitivity. If you want to rule in, you want high specificity. Okay? So based on that situation, you decide which way to go. Yes?
What are the situations where two tests in parallel?
I told you, blood bank. Blood bank. They take the blood and they do 2 or 3 tests. And if any positive, the blood is thrown out. So many of this ruling out business, certain jobs, when you're doing a screening, you definitely don't want people to. For example, you want to become an Air Force pilot. There are certain diseases you want to rule out. They go out of the way to make sure they're highly sensitive. Okay? I want to ask you a question. It's a riddle. Think carefully and answer me. There's a disease called trachoma. Trachoma, once upon a time, we knew it existed, but we didn't know how to really, culture it or diagnose it. So there's a problem. So it is a default diagnosis in many cases in the women coming with symptoms of STD-like symptoms. We used to, I think, earlier call it to non-gonococcal urethritis and all kinds of names. So it is because we are uncertain about it. It is trachoma. Trachoma, the same kind of trachoma virus, species which causes your eye problem also, is a different variety. Then finally we managed to get a test from United States. A pretty good test. A sensitivity, they said, was 95% and a specificity of 95%. As good as they come. So what we did was, we recruited 200 consecutive women attending our dermatology OPD. How many women? 200 women. And applied this test on them with the sensitivity of 95% and specificity of 95%. And it turned out that 10 of these 200 were test positive. Now, the question to you is, those who have heard this question can't answer it before. I must have said it before. For the price of a medium-sized chocolate, what is the prevalence of trachoma in this group of 200 people? Simple question. What is the prevalence of trachoma in this group of 200 women? And those who speak loud will win the chocolate. Those who speak softly will go unheard. Remember, chocolates have a habit of melting. So, who wants to guess? You guys have become more and more suspicious of me, right?
Just to confirm, 10 women were positive of the 200.
Of the 200. No men were positive. I said it very clearly. She's suggesting you I don't speak clearly. Come on, yeah.
5%.
5%. That's a good guess. Yeah. But the chocolate is still available. Go ahead. So there's one more guess possible. Say something. Maybe you will be the chocolate. And the class, you need more than anybody else the chocolate.
10%.
10%. All right. Chocolate is gone.
0.45.
0.4. All right. I know what you're trying to correct for. But sometimes, much a simpler approach you should do. Always ask the question when you get into trouble. Try to look from different angle. Okay? This is a standard rule in research methodology. Change the angle and look, change the angle and look. For example, you ask a question. What is the sensitivity?
95%.
What is the specificity? You will refuse to talk, huh? All right. 95%. But what does 95% specificity mean? It means 5% will be falsely positive. 5% will be falsely positive. That means there should be in the 200 women 10 test positives at that specificity falsely. And what did I tell you? 10 women were positive. So the best guess at the prevalence of the disease is 0. Do you follow what I'm saying? You expect when the specificity is 95%, 10 to be positive in 200. Are you following? 5, that is what specificity means. Specificity assures you there will be 5% test positives, false positive. So if I am smart, I should conclude that there will be 0. But then that brings up an issue. But this is not only in the case of trachoma. It's all there everywhere. What do you mean? That means every time you do a survey and come back with the results, you have to adjust for this sensitivity specificity. Let me give you this major problem, which you have not been taught, I know. And because people don't like this. Because When you say test positives is A plus B. This disease positive is A plus C. Total is N. Okay? What you have is A plus B by N. That is test positivity rate. I call it test positive fraction. Let me put a sign of fraction. Test positive fraction. I don't want that. I want A plus C by N, which is disease positive fraction, prevalent. That's why we do surveys. We don't do surveys to see test positive. We want this positive. How do we remove the B, which is false positive, and introduce C, which is false negative? Can it be done? Yes. And I'm going to write it there, and you're going to write it down in your notebook. So probability of disease, what percentage, this is the prevalence of disease, is equal to test positive fraction plus specificity minus 1 divided by sensitivity plus specificity minus 1. Let me give you a small problem. A test, are you with the equation is over? Got it? A test with a 95% sensitivity and 90% specificity yielded 20% test positives. What is the prevalence of the disease? Do it all with fractions, sir. Don't use percentage. Please do it all with fractions. 0.95 sensitivity, 0.9 specificity, and test positive is 0.2. 0.2. 0.11. Okay. 11%. Practically every surveys report diabetes prevalence, all are test positive. They are not disease positive. You remember writing down n factorial, r factorial and all. We won't resurrect it. Gone are those. But you don't believe me. Now the question comes up, I'm going to calculate the mean for each of them. 3 and 5, the mean is 4, 5, 6, 6, 7, 8. These are my 6 sample means. Are you with me? All right. Now, can you help me and calculate the mean of all sample means? What is the mean of all sample means?
6.
The mean of all sample means is equal to 6. Hey, by the way, what is the mean of the universe?
6.
That's also 6. Remarkable, isn't it? The universe, the mean is 6. And the mean of all sample means also 6. What does it tell us? The sample mean is an important person because he belongs to a family, the means of which is exactly equal to the population mean. So you should respect your sample mean. So even though you take only a small sample and find the mean, look at him with a lot of respect because he belongs to the family, the mean of which is equal to population mean. That is number one thing you should remember. The second point is that I am going to look at the distribution of the sample mean. Well, what do you know? I'm exaggerating a bit, okay? Have a little imagination. The sample means are crowded around population mean. Can you see that? Population mean is 6. And the sample means are crowded around the population mean. I know nobody has called 2 a crowd, but I'm going to call it. Okay? And actually, if you look at it, it has got a distribution kind of normal. I wish I had enough number, a larger universe. Actually, I could have drawn, and bingo, it would have been a normal distribution. So I want to convince you only 2 things. Sample mean is crowd around the sample population mean, and then distribution around it is normal. Just like in the case of biological samples, variability, we said no, it crowds around the mean and there's a normal distribution. So, it's good to know that something is normally distributed because then we can invoke our earlier class and say, can we then use predictions? Okay? So, I'm going to suggest that indeed the sample means form a normal distribution around population mean. And if only you have a standard deviation of sample mean, you could have put like this and said 1, 2 and said how many are in this area. The standard deviation of the sample means has got a name and it's called standard error. And there are 2 kinds of standard errors depending on what are you measuring. If you are measuring a continuous variable, it looks like this: SD divided by square root of n. That is one standard error. If you are dealing with proportions, yes, no, disease, no disease, anemia, no disease, then that looks like this: PQ by N. So you have currently, for our purpose, 2 standard error. And now let us focus on one. The story for both are same. So I'll just focus on that. Now, I don't know what the mean hemoglobin of all the pregnant women are. I don't know. But there is something like that. And that is called the population parameter. But I go and choose a small sample and come home and say my sample mean is such and such. I know most of them are crowded around the population mean. But my boss has asked me to find out what is the population mean. But I get a sample mean. Now here, just like in the case of standard deviation, one standard error on each side includes 34 plus 34% of all the samples, all the sample means. And two standard errors has 95% of all the samples. Now here is the problem. Remember, don't lose sight of your objective. You have to find where is the population mean. And you don't know where you are. You could be here, 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 and God forbid you have been a bad boy or a girl, you may be somewhere there. And you can't help it. But you should go in faith. Wherever it is, you mark your figure mentally. Then think this way I'm going to do. 95% of the samples lie within two standard errors of the population mean. So I reverse the logic. If I take the sample mean and put two standard errors, 95% of the time the population mean will be trapped in that interval. So now I say, hell, I got the sample mean as this. In our example I gave you, 10% were malnourished. What is the population value? It must be somewhere between 8 and 12. How sure are you? 95%. Okay? And that interval depends mainly on this number n. Because if you increase the n, you can get tighter and tighter interval. Because the standard error size is mainly a function of sample size. So if your boss says, I wish you had got me a finer thing, you increase your sample size. Okay? So let us do an example of it. You want to study the hemoglobin 1. Sample mean is equal to 11 grams. Standard deviation is equal to 2 grams. N is equal to 100. Put a 95% confidence interval. So what is the interval? 10.6 to 11.4. You have got these thousands of women out there. You go there and quietly pick 100 people, but make sure it is a random sample. Otherwise, this equation doesn't work. And once the random sample rolls in, you quickly calculate your sample mean, 11 gram, and then go and tell the boss, well, I am 95% confident this population mean is somewhere between 10.6 and 11.4. That is pretty good. The only thing better you can do is to examine all the thousands of pregnant women. Who the hell wants to waste your time? With 100, you have done it brilliantly. Got it? So that's why that question to you was, many people wrongly say, if I were to repeat the study 100 times, I'll get 95% of the values with. That's wrong. You won't, number one. And who the hell wants to do 100 times? What you want is, where is the population mean? And 95% confidence interval, it only answers one question. Where is the population value? Not only for surveys, for everywhere. Relative risk, odds ratio, everything. The question is, where is the population value? So whenever you get a 95% confidence interval statement, you should understand there's only one reason why you ask it. The question asks, where is the population value? Understood? Okay. Now, what you did was you took the 11 and plus minus 2 standard errors. That's what you did. Are you with me? That's what you calculated. Now I'm going to call this 2 standard errors is equal to D. And what is the D? This is called the absolute precision. I'm using the word D because all textbooks use D. Precision. The precision of the estimate of where the population mean is. In this case, it is plus minus 0.4. Absolute precision. Now, if I would write it again, your boss is unhappy. Boss says, listen boss, you did not do it right. This is too wide. Do you think it's wide? No. But he is neurotic. He wants more precise estimate. How precise? He wants not plus minus 4. I want plus minus 0.2. That is, I want it to be from 10.8 to 11.2. That kind of. No sensible person will ask for it, but he asks. How could you have done it? Could have done it by reducing the size of the sample size. Sampling error, standard error. And to do that, you need to increase the number of n. So this is the equation to see how to calculate desired sample size. He already know that D should be 0.2. Now how to get this n out? He's got a square root there. When a square root comes, my mathematics breaks down. So what do? I quietly rub it off. That's the way. So there's no more a problem. But the 2 becomes squared, ST becomes squared, D becomes squared. But no problem. Now you can take out the N is equal to 2SD square divided by D square. So assuming you want a D of 0.2, what sample size would you require? Can you calculate it? D is equal to 0.2. Sorry. Thank you. First sign of hypoglycemia. This calculates sample size. It's a very commonly used equation. And what I said, this one is for continuous variable. A more familiar one you would have seen is for dichotomous variable, which is equal to 4PQ by D squared. This is all used for prevalence studies. Again, the logic of the calculation is very simple. How precise should be your estimate? So when you go to a statistician, he'll ask you 2 questions. What is the expected prevalence? Don't shout at him. Don't tell him, that's what I want to know. No, you have to give some ballpark figure. Is it close to 50%, 5%, 80%? Something you should tell her. If you don't know, then don't do the research. Okay, you have to have some idea to do the research. So that's number 1. Second is, he'll ask for how tight should be the absolute precision, plus minus. Okay, and this is equation for, we don't have to dwell in much because people know it, but you should look intelligent in front of them. So you should say, I want a plus minus, this precision, that precision. That's enough. I'm going to stop that with the sample size calculation. Did you get a number 400? Yes. Oh, you did correctly. Did anybody not get? You didn't get? You are trying to hide behind him? No, it won't work. The D square is 0.2 into 0.2. That confuses the hell out of us, right? Right. Okay.
So, how do you choose the value of D?
Huh? How do you?
Choose the D.
Ask your boss. But I tell you one secret. When it comes to dichotomous things, like disease, not disease, prevalence of disease, incidence of, in general, it's a PQ business. There, the absolute precision is not the important one. You have to think in terms of relative precision. So, relative precision is equal to absolute precision divided by prevalence. And we usually take in terms of 20% relative precision. Let me give you an example. If I think the prevalence is 50%, 20% of 50 would be 10. So plus minus 10 would be my absolute precision. So I started thinking about relative precision. From there, looking at the prevalence, I calculated the absolute precision. In the equation, you should never put relative precision. You should always put the absolute precision. Okay? Supposing relative precision, prevalence of a disease is 10%. Again, 20% is your relative precision. 20% of 10 is 2. Okay? Plus minus 2. Perfect. So, depending on the P, first think in terms of a relative precision, and the general rule in public health, okay, it's in public health, is 20%. Because the departments usually don't have money. So you have to settle for reasonably small sample size. If you have the money, you can do anything. Okay? Okay, now I have brought in the notion of standard deviation, standard error, confidence interval, and this how to calculate sample size. For the time being, that should be sufficient. I'm going to change over. Remember, when you learn to do studies and surveys and magnitude problem, you have to do how to do accurate measurements, worry about sensitivity, specificity. There's nothing called 100% sensitivity, 100% specificity. So you have to do with it. And within the parameters, you do the survey and get the best possible result. But very often, our questions are deeper. We want to study connections. Connections in terms of relationship between various studies. In fact, one of our most important passion is to find cause for diseases. Causality. And it is not easy to think in terms of causally because we never know the whole thing. So given the little knowledge, how do you study causality? Is there a way you can streamline it? And in thinking causally, you should remember people before us also have thought of it. But there are different ways. Practically everybody can figure out causes. Okay? All of us are very good at making up this. Right. There's a book this guy is showing by Leon Goddess. Just raise it up. This guy was my teacher and a guide. You know. So I had the privilege of meeting him every now and then because guides are supposed to look at the student. First time in United States, nice to have. Very good teacher. But he told me a story. I liked it so much. And I told the story to everybody. And I hope my students will tell to their students. But remember Leon Goddess. Now, the story goes from the Second World War. During the war, the Germans started bombing the city of London. It was not a nice thing to do, but they did. And one night, the bombing was particularly heavy, and a whole building collapsed. So rescue workers went through the rubble and found a man trapped in a toilet. He was unhurt, but quite shaken. Guys asked him, "Are you okay?" The guy said, "I guess so, but you wouldn't believe what happened. I just pulled the flush and the whole building collapsed." Poor chap, he went around with the thought that he had brought down the building. But what happened was very remarkable. If human mind does this, if something is connected with another thing, in time and space, we ascribe causality. Okay? You see a boy and a girl working together, and it comes naturally to us. Okay? So we connect up, we make stories in our mind. Can't help it. And our life is full of stories. Okay? And chicken causes heat, potato causes gas, and the world is full of these stories. How do you figure out which is real, which is not real? Now remember, the problem is, just by coincidence, just by chance, things can happen. But then you say causality, okay? You connect it up. And I don't know how many times I do it, you also do it. Especially if you know how to play cards. Have you seen card players praying, God, give me a good card? I don't think God is waiting to give you a good card. But when it comes, thank God, okay? So, this is the way our system works. You need a cause. If you can't find a cause, you ascribe to God, whatever it is. And that is the human mentality. But our science should be something greater than pulling the flush, okay? Something of quality. Is there a way of doing it? Plato was a student of Socrates, thought that all knowledge was within you. Wow, that's nice, right? Yeah, you're born with it. You don't have to come for a course and think like that, okay? Go, find some nice tree, sit under it and meditate, and it'll all come out. So epidemiology causes a waste. It's all inside you. And that group of thinkers is called rationalists. Rationalism. The other group was headed by his student. You know Plato, where is he from? Which nationality was he? Anybody? The Greek. Yeah, that area was busy fighting wars, everything. But Plato did a smart thing. He went out of Athens, just outside the city. He built a university. Okay? And that university was there for so many years. Plato was before Christ, okay? And Aristotle was a student. Aristotle also taught Alexander the Great when he was young. So we have an Indian connection there. But what I'm trying to say is, Aristotle said, no, Plato is wrong. See, those days a student could tell this professor is wrong. Not now. Plato allowed it, okay? He said, knowledge is not within. You have to observe, measure, collect data, and then you become knowledgeable. So there are two schools. This one is called, Plato's thing is called rationalism, and Aristotle's thing is called empiricism. The study design that we do everywhere is called empiricism. But that's not what Plato was thinking of. And I remember the beginning of the class, I tried to bring out the meaning of the word fact and theory. And that is what the reflection of this combat is. Always thinking of where does the truth come from? So you can imagine Plato's line like a spider sitting in a corner, weaving his own web. Or Aristotle asking, like an ant, collecting data. Okay? But I think the true knowledge must be a combination of the two. Like in the case of a bee, collects nectar, and from the nectar creates the honey. So both are important. But I mentioned all these because behind all this there is a logic. The logic has got two domains. One is called deductive logic, another is called inductive logic. Deductive logic follows from rationalism. Inductive logic follows from empiricism. We all use it. For example, deductive logic. I went into a room, there were 400 people sitting there. And I said, at least 2 of you must have birthday on the same day. Could I be wrong? Birthday, Gandhi Jayanti on October 2nd. Could I be wrong? Huh? Possible? Impossible. That is the beauty of deductive logic. Because In that statement, I used two axioms. There are 400 people sitting in the room, and there are 366 days in a year. If both are true, then what I said must be true. Because I assigned January 1st for one person, January 2nd for... After 366 days, I have run out of days. I have to reuse a day because there are 400 people sitting there. So when I make a statement that way, it has to be true. In medicine, this is a mainstay of any logic. In creating new hypotheses, new paths, deductive logic is important. How does that inductive logic come? Data, collect data. For example, I want to know what is the color of a crow. How do I do it? I take a lot of paper, pencil, go out and crow, black, crow, black. After having seen 125,344 crows, I would say all crows are black. And then I'll put it in a cover and post it. And as I turn around, a white crow passes by. Okay, what the heck? Are there white crows? Huh? Yeah, albino crows. But crows are very racist. The black crows don't let the white crows survive. Okay? So, anyway, the point I am trying to say is this. Axioms generally come from empirical data. So that is the source of our knowledge. But the wisdom is how to mix the empirical data and rationalize it to know the truth. And that is very often not seen properly. In other words, we need not just p-value significant to know the truth. It is never the truth. Okay? You have to take that and take further and say, what does it imply? So that is what we are going to search for. But I want to tell you something else in this context, in the evolution of science. Once upon a time, in Europe, all source of knowledge was with the clergy, Catholic priests to be specific. If you have any problem, you go and ask them, he'll tell you. And that will be the truth. I suppose in India also we had sannyasis where you went. So we went to them. But one morning, one guy called Fracastorius, have you heard that name ever? He woke up with a new vision. He said, I know what causes disease. I said, how? What is that? He said, there are small animals whom you cannot see with the naked eye. They cause the disease. Wow. If a priest says, it must be correct, right? And he gave it a name also, the theory of contagion vivum. The prevalent thought those days was something called miasma. Miasma means bad air, bad environment. Now started the battle between contagion vivum and miasma. Today we can sit and laugh at them because we know both play a part. But that time they wouldn't talk to each other. If the miasma guy had a pretty daughter who wanted to marry somebody from the contagion vivum group, no way, no, you are not marrying my daughter. That was the stubbornness they had. They fought and fought. In fact, I think Istanbul, where Ashish is going to Istanbul, no? There was an epidemic of plague. And they have sent, both groups went to investigate. And what did they come out with? The miasma group came with the impeccable evidence to know it is bad environment. And what about the contagion vivum group? Terrific evidence to show it is a small animal which cannot be seen by naked eye. Then came Louis Pasteur. Have you heard of Louis Pasteur? Which country? France. Okay. He was a true Frenchman. All his research, he was not a doctor, but he contributed tremendously to medicine. Everything with a focus on France. So he was always that French-oriented kind of person. And he showed, there are some little fellows you really can't see, but they cause disease. He showed it brilliantly. Okay, these are stories you should read about. But by the time, this Leeuwenhoek fellow had been meddling with the microscope. So people became more and more available, and people could actually peer down and see this little animal, okay, which caused disease. And then came the era of bacteriology. Everybody wanted to become a bacteriologist. You ask a mother, what is son doing those days? She say, bacteriology. Like in here in India, 5 years ago, software, so this particular trend came on, and poor fellows, the miasma group, they had to go back to church, okay, quietly and sit at the back. We are wiser now how these things combine. But the problem was, everybody was diagnosing or detecting, finding cause. Headache germ, backache germ, you name it, there are germs everywhere. And what to do? How do you know there are germs causing the disease? And Robert Koch and Henley came out with some rules. Koch's postulate. Heard of that? Anybody remember them?
You should be able to culture it, and it should re-cause the disease if you...
So there are two observational criteria, and the third one is a cruel experimental criteria. She remembers only that. Like most of us do, only the cruel one. That is, you sneakingly take it out, culture it, and when the other fellow is not watching, give a dose. And make sure he falls sick. And then you know it's a cause. But the first two are the more important one for observational sciences. And the first one is, the agent should be present in every case of the disease. Number two, agent should not be present in the absence of disease. And I'm going to put it down on the table because that should be important. The epidemiologists all, without exception, keep depending on 2 by 2 table. We are incapable of complex thinking, okay? And so we do this 2 by 2 table. What I just now said, I'm going to put it in a 2 by 2 table. Disease present, disease absent. Agent, that is the bug, present, absent. A, B, C, D. Many of my students suspect I know only 4 alphabets in the alphabet, 4 letters in the alphabet. Because A, B, C, D. It keeps coming back again and again. But look at this. First postulate demand. In every case of the disease, agent should be present. That means C should be 0. Number 2, agent should not be present in the absence of disease. The fellow hang around everywhere, then you can't call it an agent. So that means B should be 0. This is the true criteria. Who presented? Koch's postulate demanded. Now, look at it again. B is equal to 0 means if the agent is there, you have to have the disease. There's no escape. In other words, it is a sufficient cause. What about this one? C is equal to 0. Without agent, you can't have disease. That means the necessary cause. So, Koch's postulate said, If you want to confirm a particular agent causes a disease, then you have to say, prove that is both necessary and sufficient. Now, any of you know a disease like that? Good, there isn't one. Okay, now I tell you one thing. All infectious disease have a necessary cause. But to make it sufficient, difficult. TB doesn't cause tuberculosis. You have to have other plethora of evidence. So we realize this is in big trouble.